What's up, everybody? It's Dan from SageMathTutoring.com, and I'm back with another video, this time pertaining to parametric equations, vectors, for the AP Calculus BC exam. So I say we just get right into it. Just going to go over a couple problems here. So the table gives coordinates of a particle moving in a plane along a smooth curve. Find the average velocities over the time intervals of 0 to 1, zero point 0.5 to 1, 1 to 2, and 1 to 1.5. Now, the process to find the average velocities will be the same for all of these, but I'm just going to, in the interest of saving time, I'm going to only just do it for this one, but just know that what I do for this one is going to also apply to these. So here's a list of concepts that you do need to know for the parametric equation type problems and the vector type problems for the AP Calculus BC exam. And this talks about velocity here, so there might be a temptation to think, oh, I guess I'm going to have to find the derivative, you know. However, we don't have a function that we can take the derivative of. We just have a table of values here. So we're going to have to rely on another method. And the method really would be just taking advantage of the fact that velocity is really just a change in position over the change in time. So we certainly have the change in time. It goes from 0 seconds to 1 second, which is from here to there. But all we need to do is figure out, well, what is the change in position, and then what is the change in time? So we could do that by finding the average velocity as it pertains to the x component. So that would be a matter of recognizing that from 0 to 1, when it comes to x, I'll put a little sub x there. We are looking at 4.5 minus 2.7, and then that would be all over 1 minus 0, and that would end up becoming 1.8. All right. Now that's as it pertains to the x component. Now when it comes to the y component, we are looking at the following. It would be 6.0 minus 9.8 all over 1 minus 0, and that becomes negative 3.8. Okay, so there's two ways of expressing this, and this is pertaining also to a question that my student actually had about this stuff. It turns out that there are two ways of expressing this answer. One is to use component form, where you would literally take into account, the x and y stuff. And really, in reality, this would really just be the velocity. So it would be dx over dt, if we were to be specific about it, and dy over dt. But the real point here is that you could use these weird looking brackets to express the answer, or you could use the whole INJ language. Now, if we were to use these weird looking brackets, I think you understand it would be a matter of writing 1.8 comma negative 3.8. If we were to use that INJ lettering, you would start with the first number, which is 1.8. You'd say I next to that, and then you'd say minus 3.8j. All right. Now, the reason for that kind of language is beyond the scope of this video. It does have something to do with a sort of unit vector here stopping at 1, and a unit vector here stopping at 1. And we would call this one I, and this one J. So it has something to do with that. There are plenty of YouTube videos that get into the details of that. So feel free to check that out. I could even link one below. When it comes to 1b, estimate the velocity and speed of the particle at t equals 1. Okay, well, first of all, they're mentioning speed here, right? Now, for speed, we would need to use this here. So what we're going to do is we're going to find the average velocity at t equals 1. We're going to figure out the components of that, and you're going to put the x component into this position and the y component into this position in order to figure out the actual speed. Okay, so here's a case, since they're asking about speed, where we actually do need to rely on one of these sort of structures, one of these concepts here. All right, now the question is though, okay, well, how do you estimate the velocity at t equals 1. Well, one way to go about it, I'm not sure if my student's teacher would insist on a different way, but one way of going about it for sure is you can find the average velocity between these, between zero point 0.5 and 1. Then you could find the average velocity between 1 and 1.5. And then you can just take the average of that. All right. So in other words, just divide by 2 after that. All right. So if we were to do the average velocity, let's say from 0.5 to 1.0, as it pertains to the x, that would most definitely be, let's see, 4.5 minus 3.5 all over, looks like it would be 1 minus 0.5, and that's going to become 2, all right, and that's pertaining to the x component. When it comes to the y component during that very same time interval, we'll put a little y down here. Of course, we are looking at 6.0 minus 7.2 all over 1 minus 0.5, and that would give us negative 2.4. Okay, so the average velocity through the time interval of 0.5 to 1.0 could be expressed as 2i minus 2.4j. Okay. Looking further, we could now analyze from the time interval of 1.0 to 1.5. That would be, as it pertains to x, that would be, let's see, 5.9 minus 4.5 minus 4.5 all over 1.5 minus 1, and that's going to give you 2.8. All right, now as it pertains to the y component, if we were to analyze that time interval, we would have, it looks like 6.4 minus 6.0. That would be all over 1.5 minus 1, and that should give us 0.8. Okay, so that answer could be written as 2.8i plus 0.8j. So what I'm proposing is that we could then take the average of that. Okay, we could take the average of that, and that would be a matter of sort of adding 2i minus 2.4j plus 2.8i plus 0.8j, and then dividing that result by 2. And that's going to end up giving us, let's see, so we'd have 4.8i divided by 2, so it's going to be 2.4i. We would have, if I was to combine negative 2.4j and positive 0.8j, that would be negative 1.6j, and negative 1.6 divided by 2 is negative 0.8j. Okay, so I'm just kind of doing it all at once, all right? But it would be a matter of combining like terms and then dividing the top, or dividing every term, we could say, by 2, all right? So in other words, this could be said to be the average velocity of the particle at t equals 1. You could also express the answer as this sort of 2.4 negative 0.8 as well. Now, as it pertains to the speed at t equals 1, well, again, you can rely on this structure here, so I'm going to rewrite the big structure. It's going to be something squared plus something else squared. Of course, this is basically the distance formula. And when it comes to, this is going to be the x component of the velocity squared, so that's going to become 2.4 squared. and y component of the velocity, so of course that's negative 0.8, and we would be squaring that. And then that whole thing would end up becoming 2.53 approximately. So I'll actually switch this to approximation symbols. Okay, so that would be the answer to the speed question. So here's the average velocity at t equals 1. Here's the average speed at t equals 1. Hopefully that makes sense. Okay, the position vector of a particle is given by r of t equals t squared, comma 5t. When is the speed a minimum? So what we could do is recognize that, of course, we're dealing with speed. So we would be dealing with this structure right here. Since we want to figure out when the speed is a minimum, we could actually take the derivative of this and then set it equal to 0, and then kind of do like a sign chart from there. Okay, so that's a way to go. Well, of course, if we're going to use this, we're going to have to do, dx of dt and dy over dt. So let me kind of write that off to the side. Dx dt, it's going to be the derivative of t squared, which is just 2t, and dy with respect to t is going to be just 5. So it's actually not too bad. And then if you were to plug that into that structure there, we're looking at something squared plus something else squared underneath here. And of course, it's going to be 2t, and we have 5 as well. Okay, so simplifying further, we're looking at 4t squared plus 25. And I think everyone acknowledges that this is the speed, so I'll write s equals. And then the reality is that this could be rewritten as 4t squared plus 25 raised to the 1/2 power. At that point, we could go ahead and take the derivative of that. And that should be a chain rule scenario. So we're looking at s prime equals 1/2 times 4t squared plus 25 raised to the negative 1/2 times the derivative of what's inside the parentheses, which is going to be 8t. So at that point, we're looking at 8t all over 2 times radical 4t squared plus 25. And if we set that equal to 0, we would quickly realize that t would therefore equal 0. I'm also seeing that even without taking the derivative of this, we could have recognized that this speed function is a square root function that has no vertical transformations whatsoever. It doesn't shift up or down. So there's no vertical transformations whatsoever. So it makes sense that the minimum y value, or we could say the s value, the minimum s value of this function is definitely going to be 0, because the square root function, at least the parent function, looks something like that. So it's not taking into account any horizontal shifts or whatever, but the parent function, let's say, this guy, looks something like that, and clearly the minimum is at 0, so long as there's no vertical transformations. That's the case here. Okay, sketch the planar curve with the given vector equation. All right, so first let's do that, right? They're asking us to do a lot of other things, but we're going to sketch the planar curve. So one way of going about it, or perhaps the way of going about it, is to recognize that the cosine of t corresponds with x, the sine of t corresponds with y. Whenever you're dealing with cosine and sine as the vector, there's a good chance that you're going to need to sort of turn that into like a circle, okay? So in other words, we could write down, okay, whatever, x equals cosine of t, y equals sine of t. It is also the case, for the record, that sine squared of whatever plus cosine squared, that's going to equal 1. That's like the Pythagorean identity. Now we could use substitution and therefore say that y squared plus x squared equals 1, and then we can rearrange it to say x squared plus y squared equals 1. Now that is the equation of a circle that is centered at the origin and has a radius of 1. So that's super helpful. So we have our xy coordinate plane, and essentially it's just a unit circle, right? It's just a unit circle. So that's cool. Then they say find r prime of t. That should be easy enough. That's just to take the derivative of both of these components. So I'll do that up here. R prime of t is going to equal negative sine of t, cosine of t. And we want the, so we satisfied that part. Then they say sketch the position vector r of t for the given value of t. So we want to sketch the position vector r of t at pi over 4. Well, the position vector is given by this r of t thing here. So all we would have to do is plug in pi over 4 into that. And I'll just write r of pi over 4 is clearly equal to, that's going to be radical 2 over 2, comma radical 2 over 2. Now, what does that mean? Well, that means that you're dealing with this vector here. And it is the case that that vector is going radical 2 over 2 over, that's the x component, and it's also going radical 2 over 2 up, so therefore this point you could say is radical 2 over 2, comma radical 2 over 2. All right, so that is the case with that. What else? So they also want us to sketch the tangent vector, r prime of t. So that's pertaining to this information here. So the slope of a tangent line to a curve, which is essentially the tangent vector, is this. It's dy over dt, which you can get by putting dy over dt all over dx over dt. Now, I didn't really use the sort of label for it, but this was the dx over dt, and this over here was the dy over dt. We already found that when we figured out what r prime of t was, right? R prime of t. They asked us to find that. We did. Well, what did we do? We took the original, position vector, and we found the derivative of that. So that's dx with respect to t, and then we did dy with respect to t. That's right here. So according to this, we're going to be putting the dy with respect to t over the dx with respect to t, and that would result in cosine of t all over negative sine of t. Now, however, we of course are going to be substituting in pi over 4 for t, and kind of move this graph over a little bit. That would result in this scenario where it's cosine of pi over 4 all over, we'll keep it negative down here, negative sine pi over 4. Now that's going to equal radical 2 over 2 all over negative radical 2 over 2. And that's going to turn into negative 1 if you were to do the math. So that is that's the slope of the tangent line. Now, a slope of negative 1 over 1 means you're going down 1 over 1, right? You're going down 1 over 1. So therefore the x, if we were to turn that into sort of a vector, the x component would be positive 1 and the y component would be negative 1. You could also call that I minus j if you're going to use that, okay? So that's the tangent vector, but it's not so much that they asked us to write the tangent vector, they did ask us to sketch it, right? They asked us to sketch it. So that's going to be a slope of -1, dropping off of this point here. Okay, and by the way, it makes perfect sense. I mean, it doesn't it make sense that the tangent line would have that perfect -1/1 slope? So that's the tangent line itself, but if we're going to be doing this vector, we could think of the vector as originating from that point radical 2/2, comma radical 2/2. All right. So this red vector is the tangent vector. We just sketched it. All right. So that is how you do this problem. So notice what was involved? What was involved with that? Well, sketching, you needed this insight about the Pythagorean identity, right? X equals this, y equals that, and then you recognize, oh, I'm dealing with a circle. Huh, interesting, right? So you draw your circle, turned out to be a unit circle. R prime of t, not a big deal. That's literally just doing this. Sketch the position vector. R of t, nothing more than plugging pi over 4 into the position vector itself. Tangent vector was a matter of acknowledging the slope of a tangent line to a curve, and that's based off of this information. So we did need this, right? As dy with respect to t over dx with respect to t. So that was important. You definitely needed that. So anyway, so for my student watching, hopefully this was helpful. These are the 3 problems that we were looking at the other day. And for the rest of you watching, hopefully it's helpful as well. And if I made any mistakes, I don't think I did, but if I made any mistakes, go ahead and comment below, let me know. And I will talk to you everybody later. Take care. Bye.